Hello everyone, and today we'll be talking about uncomputability and reductions. Reductions are a key idea in the latter part of CS 121, and it's a proof technique that's used all over the place there, so hopefully this will be good preparation. So before we go any further, last week we talked about a very sort of granular level of programming and what does it mean for there to be a computer, and we thought about NAND and Turing machines, and that's all well and good and really helped us for a lot of reasons. Like last week, you considered why we had to do that instead of just thinking about Python. But this week, we're less investigating questions like what is a computer, and we're more investigating questions like how hard are problems given our reasonable model of computation. And actually, a result that you'll prove in 121 is that Python is actually the same power as like Turing machines and stuff like that. So using that result, we're just going to use Python, or you can use any programming language that you're comfortable in, or you can even just use pseudocode, just like sort of high-level code to summarize what a program is doing. And we'll use that. So when we say, write a program to do this, you don't have to like write out lines of NAND and stuff like that, because that's really not a useful exercise. You don't learn anything from that. You can just write out the pseudocode or the Python for it. Because the questions we're going to be asking are like, can you compute this like efficiently, or can you compute this at all? And those questions are sort of the same up to constants, regardless of if you use Turing machines or Python, and it's a lot easier to use Python, so that's why we're doing that. Great. So a new question is, when we talked about NAND, we showed that NAND was universal. In other words, we can compute any finite function with NAND. But Turing machines can compute any functions, right? They don't have to be like fixed length inputs and fixed length outputs. So we might ask the same sort of question about like any function with any size input and any size output. Can we still solve all the problems? Like, is every function still computable? And I give you a hint, the answer is no. So here's an example of a problem that we can't solve. This is called the halting problem. So let halt be a function that maps from, remember this set is finite length binary strings, to 0, 1. And it's going to be taken one argument that we'll just split up into two arguments, right? And the first part of the argument will be some Turing machine M, and the second part of the argument will be some input X. And just as an aside here, you might be like, how can you pass in some Turing machine as part of a binary string? Well, that's a great question, and you go over this in more detail in 121. But thinking about if you have some Turing machine, right, maybe we write out the description in like words or mathematical symbols, right? And then you could just like use like an ASCII representation. When you like type all that stuff up on your computer, it's all stored as bits, right? So we just pick some way to represent like mathematical symbols and letters as bits, and we say this is how we're going to do it. And now we can represent any like Turing machine that we can write out. Well, we could just use the bits that represent it, and we can pass that to the function. So the idea is you can really store anything in binary using encoding. So we'll pass in some Turing machine and some input to that Turing machine, and halt will return 1 if the Turing machine M halts on input X. Recall that in our initial definition of Turing machines, right, the Turing machine could actually go on forever. It could just keep going left to right, moving around, like exploring the tape, and it could never halt. And so this is actually like a highly relevant question. You might want to know, when we start running this computer program, for example, if you write some Python program, right, you might want to know, is it going to halt, or will it go into an infinite loop somewhere? Because if it's going to go into an infinite loop somewhere, you got to like take precautions, and maybe you have to stop it after a certain amount of time. So this would be a really useful question to be able to answer. But this theorem shows actually we can't do that. And actually, you'll see in 121 that there's a whole bunch of like semantic properties of programs. When I say semantic, I mean sort of just like related to like the meaning of the program, like what it does to inputs and outputs. Like, does it halt? Does it halt on 0? Does it, always return an even number or something like that? Like things that you might want to sort of be able to talk about at a high level of programs. Like a lot of that stuff is not really analyzable. And this all comes from sort of the reduction techniques that we're going to use. Great. So first, I want to give a proof that halt is uncomputable. This is more included for completeness, like it is in 121, but I don't think it's really the most important material to learn this week. So if you're sort of in a rush, or you can just skip this part, or if you want to watch it and you don't quite get it because it is a pretty dense proof, then you're welcome to just move on to the next sort of stuff. But I wanted to put it in here in case you are curious. So suppose towards a contradiction, remember, we're trying to prove that halt is not computable. So we're going to suppose we have some function like halt p, and halt p is going to be some program that computes halt, right? So it'll take in two inputs like some m and some x, and then it'll return either like 1 or 0 depending on if m halts on x. So now we're going to design a new program, and like remember we're writing code in Python, right? But as we said, like Python is equivalent to Turing machines, so when we say like we could just turn this program into some Turing machine and then feed it into halt p anyways, which is basically what we're going to do. So we're going to define some program f, and what it's going to do is first it's going to just take in a singular input, and then it's going to run this program halt p, right? Because on its input twice. So basically it's going to take its input, it's going to say treat its input like a Turing machine, right? Treat its input like a Turing machine here, and then evaluate its input on itself. So if you thought of the input as a Turing machine, and then you fed that Turing machine, like the code of that Turing machine, check to see if that would halt. And if it would halt, then this program is just going to loop forever. Otherwise, this program is going to halt and return 1. And we're going to run into a little bit of a problem, right? Because as we said, remember, you can just take Python code and you can turn it into a Turing machine, right? So let Z be the Turing machine that does all of this, right? And now let's try running halt p on Z and Z. And this is a little bit confusing. What does this exactly mean? So it means we're running halt p on Z is some Turing machine. And then remember, as we explained earlier, like we're representing this Turing machine as bits. So we're just going to take those bits and we're going to put them in again. Because you can run a Turing machine on anything. So we're saying take this Turing machine Z and run it on its own code. So now we can prove by casework that halt p does not actually calculate halt, right? So what we want to show is that halt p is not equal to the behavior of f of z, right? Because so if halt p is correctly computing halt, then like if this thing returns 1, then like when we run f on z, we should see it halt. And if this thing returns 0, then we should see like f of z not halt. So let's break this up into cases. First, let's say that halt p of z on z equals 1. So according to our program, if we run z on itself, we'll get 1, right? So if we run z on z, what are we doing? Well, it literally means we take this program and we run it on z, right? So essentially what we're doing is we're running f of z. And this says, well, that will halt. Well, actually, if halt p of z on z gives us 1, well, then this will be 1 right here, and actually, we'll just loop forever. So it doesn't agree with the behavior because the halt p program tells us, oh, z is going to halt when you run it on itself. But when you actually run z on itself, right, like if you were to do f of z, because z is the Turing machine that computes f, then you would actually get, oh, this is supposed to loop forever. So then the other case is that halt p of z and z equals 0. But if halt p of z and z equals 0, similarly, what is the what happens when you evaluate z on itself? Well, then halt p is 0, so we don't do this first thing. We actually just do the second thing and we return 0. So in this case, it actually halts. And so again, it does the opposite of what it's supposed to. And so we see that, therefore, halt p cannot compute halt. Because regardless of what it returns, it's returning something that actually doesn't summarize the behavior of the program, right? Like, in order for it to compute halt, it has to return 1 when the Turing machine halts on input X. But in this case, it's returning, if it returns 1, it actually means the Turing machine doesn't halt on input X. And if it returns 0, it means it does halt. So we found an input for which it does not calculate the same thing as halt. So the logical question to ask is, what other functions are uncomputable? And there are actually a ton of uncomputable functions, but not all of them have quite as succinct proofs as was presented on the previous slide, and also is a little bit of a dense proof, so it might be sort of hard to come up with the proofs for these other functions. And so we wish we had a little bit more of a systematic approach, like a proof technique that we could apply to prove a lot of different things are uncomputable, and that's what we'll introduce this week. It's called a reduction, and in a second after I explain what we'll be doing, I can explain better why it's called a reduction. So let's take a look at the function that we're going to prove is uncomputable. We're going to prove halt on 0 is uncomputable. And halt on 0 is a function that takes in some Turing machine m and returns 1 if and only if m is a Turing machine that halts when given 0 as an input. So in other words, halt on 0 of m returns 1 if and only if m halts on 0, as the name implies. So in a reduction, what we're going to do is we're going to reduce one problem to another. In other words, we're going to say solving this problem A is as easy as solving this problem B. So in this case, we'll say solving halt is as easy as solving halt on 0. In other words, if we could solve halt on 0, then we could solve halt. And this will help us prove that halt on 0 is uncomputable, right? Because this is basically a proof by contradiction. We're saying, suppose towards a contradiction that we could compute halt on 0, then we could also compute halt. But since we know halt is uncomputable, therefore our initial assumption must have been wrong, and actually we can't compute halt on 0. Right? So by reducing the problem of halt to just solving halt on 0, we can show that, oh, well, therefore halt on 0 must also be uncomputable. And whenever you do sort of this type of reduction, there's always a couple of steps. So step 1 is describe the reduction. So in other words, describe how we're going to solve halt with halt on 0, right? So we're going to suppose towards contradiction that halt on 0 is computable. So we'll use this function, and I'll call it halt on 0 oracle, that we're going to assume computes halt on 0. Then we'll write some other function, or some other program, compute halt, using calls to halt on 0 oracle, right? And to give you a little preview of what we're going to do, right below here, we've written a program, compute halt, that computes halt, using halt on 0 oracle. And that's what we mean by reducing the problem of halt to halt on 0, because we're saying if we had something that could solve halt on 0, then we could solve halt. And the reason we're calling it halt on 0 oracle is we often refer to the solver for halt on 0 as like a black box or an oracle. And what we mean by that is we really don't care how it solves halt on 0, right? Like it could just be like a magic box that just tells us the answer to halt on 0. Anything that solves halt on 0 will allow us to solve halt. And that means that there must be no way to solve halt on 0, because if there was any way to solve it, then we could solve halt, and we know that we can't solve halt. Great, so after we've created the reduction, then we'll actually have to analyze the reduction. So in that case, we'll have to actually prove that this function or this program that we created, compute halt, actually computes halt. So we're going to go ahead and do those 2 steps. So first, let's describe the reduction. And now I've written a program that I say computes halt on the left side. So it's going to take in, just like halt, it's going to take in some Turing machine m and some input x. And then we have to think about what we're trying to do here. So basically, when we're computing halt for a person, we are getting in a Turing machine and an input, and we're trying to give them the answer of does m halt on x, right? But all we have is access to this halt on 0 oracle function. And the halt on 0 oracle function can't tell us does m halt on x. All it can tell us is does m halt on 0. So that's not great. So instead what we're going to do is we're going to create some other Turing machine p, and that Turing machine p, its behavior on 0 will be exactly the behavior of m on x, right? So it's going to take in some input y, and it's actually just going to totally disregard this input. It's going to run m of x, and it's going to return 0. So what does this mean? Intuitively, this means that like if m of x halts, then p evaluated on anything, so p evaluated on 0 is basically just return 0. So if m of x halts, then p will just halt on 0. And if m of x doesn't halt, well then if you evaluate p on 0, then m of x will just run forever and p of 0 won't halt. So we've basically created a program that halts on 0 if and only if m of x halts. And that will allow us to use our halt on 0 oracle function, which tells us if a Turing machine halts on 0, to analyze if m halts on x. That's the description of the program would just be like writing this down, and then maybe giving some words about what it's doing. Say we're creating some other Turing machine inside P, and then we're feeding it to this thing just so the reader knows. And then the proof will actually be following a lot of the logic that we just talked about. So now the proof is demonstrating that compute halt computes halt, right? So in other words, we're trying to show that compute halt of m of x equals halt of m of x. So we can split it up into two cases. So case one is that m of x halts. So if m of x halts, then p of 0 runs m of x and then returns 0. So p halts on 0. So therefore, this last line here will return 1, because this last line analyzes if p halts on 0, and p does halt on 0. So this returns 1, which is exactly what we want. So the other case that we have to check is if m of x does not halt. And in that case, then p of 0 runs m of x, which never stops. So p of 0 never halts. Therefore, this line returns 0, because this line returns if p halts on 0, and p does not halt on 0 in this case. So we see that in both cases, it agrees and computes halt correctly. So that completes our proof, right? Because, again, this is a very important proof technique in 121, so I want to make sure the intuition is really clear for what we're doing, because this shows that halt on 0 is not computable, because we said, suppose we could compute halt on 0. Suppose we have this function this program halt on 0 oracle that computes the function halt on 0. Then we use that to construct another program, compute halt, which we just showed computed halt. And that's a contradiction, because we know halt is uncomputable. So this proof technique will come up a lot when you're trying to prove that things are uncomputable. Like if you want to prove that some function f is uncomputable, well then say reduce halt to f, or reduce something you know is uncomputable to f, which is to say show that if you could compute f, then you could compute something uncomputable, and therefore f must also be uncomputable. And you can follow these steps again.